invitation.
Yeah, great.
Let me repeat that. Thank you, David, for the invitation. So, right. So I've hidden the participants so that I can see my screen. So that means if you raise your hand or something, you probably won't see. So probably if you just interrupt me, please, with questions. So the title, as you just heard, is Summing Over Bordisms in 2D TQFT. Let's see, I should hide the video panel, I think. Okay, and so this is work with Anindya Banerjee, and that appeared in a paper about a year ago. And since then, there have been some follow-up discussions that are in progress with Daniel Friedan and Shiryar Sikandar. Anindya, by the way, will be in London as soon as he gets his visa problems settled. So here's the outline of the talk. I'll start with some motivation, talk about some reminders on TQFT, and then we'll come to this main property I want to stress today, which is the splitting principle. So the motivation. So the motivation comes from a long-standing problem in quantum gravity. Now, I don't know what quantum gravity is, but presumably it's something like computing probability amplitudes by summing as in a path integral over metrics on some space-time. I think someone isn't muted, so you should please try and mute yourself. So summing over metrics on some space-time. And we would be waiting with something like the Einstein-Hilbert action or some modification thereof. And the question, the longstanding problem in quantum gravity is, if we sum over metrics, should we also sum over topologies? Now, there's a model for quantum gravity called the ADS-CFT correspondence. And in that context, there are some puzzles when you include non-trivial topologies. So very roughly speaking, the ADS-CFT correspondence claims that if you have a hyperbolic manifold with a boundary, then somehow quantum gravity on the hyperbolic manifold is equivalent to quantum field theory without gravity in the conformal boundary. And the initial examples all had a connected boundary. But there are, of course, hyperbolic manifolds where the boundary has multiply connected components. And it was realized soon after the ADS-CFT correspondence was proposed that this leads to puzzling aspects. And then more recently, there was a paper of Saad, Schenker, and Stanford, which considered the sum over topologies in a certain two-dimensional model of quantum gravity called J2 gravity, which is much more amenable to solution than the four-dimensional version. And they identified the results in that with results that you would get from a matrix model. But that raised conceptual questions because a matrix model is an averaging over Hermitian matrices, which is essentially taking an ensemble average of results in a quantum mechanical system. So in this two-dimensional case, the holographic dual would be one-dimensional quantum mechanics. And a matrix model is averaging over Hermitian matrices. So it's an ensemble of one-dimensional quantum field theories. So motivated by these issues and other recent vigorous discussions, Don Marolf and Henry Maxfield considered a curious topological model of 2D gravity. And an essential part of their discussion involved summing over topologies with disconnected components. So my project with Anindya Banerjee was motivated by the desire to understand this Marolf-Maxfield model in terms of standard topological quantum field theory, because if you look at their paper, you'll see that it's not really written in a way that's very accessible to mathematicians that work in topological quantum field theory. So that was our project. So let me just give some brief reminders on TQFT. What is topological quantum field theory? So let's begin with a definition of a bordism. So let X in and X out be smooth, compact manifolds of dimension d minus 1. Then we say a bordism Y from X in to X out is a d-dimensional manifold together with a choice of a disjoint decomposition of the boundary of Y into what we can call the ingoing and outgoing components, together with diffeomorphisms of the ingoing component of Y, the boundary of Y to Xn and outgoing to X out, and embeddings of collars around Xn and X out into Y, which reduce to the specified diffeomorphisms on the boundary of Y. So here's a simple example. Suppose Xn is a zero-dimensional manifold consisting of 3 points, and X out is a zero-dimensional manifold consisting of 5 points. Then this blue manifold, this blue one-dimensional manifold with boundary, is an example of a bordism from Xn to X out. Notice there are no orientations. You need not introduce an orientation. Of course, we could also talk about oriented bordisms, but we don't have to. So anyway, there are 105 such pictures, and actually there are infinitely many bordisms from X in to X out, because we could include infinite numbers of arbitrary numbers of disjoint unions with circles. Now, bordisms are morphisms in a category, the bordism category of d minus one dimensional manifolds and d-dimensional bordisms between them. And for purposes of this talk, a topological quantum field theory is just a monoidal functor, Z, to the category of vector spaces over field kappa. So the basic idea is that if I have a spatial manifold X, then the functor applied to X is a vector space, and that's the vector space of states, quantum states associated with the spatial manifold. And the monoidal structure means that if I take a disjoint union of manifolds and apply Z, then I get the tensor product of the state spaces. So now if Y is a bordism from X in to X out, then the functor Z of Y is a Z functor applied to Y. Z of Y is just a linear transformation from the ingoing space to the outgoing space, in such a way that if I compose bordisms, I compose the linear transformations. So now, recall that we can have different bordisms between a fixed ingoing and outgoing spatial manifold. So supposing we're given a topological quantum field theory, which I'll call the seed TQFT, then we can define what I'll call the summed amplitude, at least formally we can, where we sum over all bordisms between X in and X out for fixed X in and X out. We sum the amplitudes Z of Y. And we should divide by an order of an automorphism group. And the automorphism group that we'll use is that of the homeomorphism type, which restricts to the identity on the boundary component. Now, when I've given this talk in the past, for example, Maxim Kontsievich objected at this point and said, well, he didn't think that that was the best way to weight the bordisms. And actually, something under discussion with Daniel Friedan, Shariar right now is, and Anindya is whether there are other ways of weighting the bordisms that are physically interesting. But this is what's in the literature, and so this is what I'm going to stick with today. Okay, so if we sum over these bordisms, then each Z of Y is just a linear transformation from a fixed vector space, Z of Xn, to another vector space, Z of X out. So if I sum linear transformations, I just get another linear transformation in Hom ZXn ZX out. So this formulation raises some questions. Does the sum exist? If it exists, is it computable? What properties does it have? And can we extend it to fully local TQFT? So far, I've only considered TQFT at the top 2 levels, D and D minus 1 dimensions. So some answers to those. Well, yes, it exists for 1 and 2 dimensions, at least, and it does not exist for 3 and higher, at least not in the most naive sense. And that's a really interesting open problem. What to do about that? In 1 and 2 dimensions, in all the examples we've considered, yes, it's computable. What properties does it have? Well, that's a very open-ended question. So the property that I'm going to be focusing on, and this is the main focus of this talk, is something I'll call the splitting property. And for 2 dimensions, at least, there is an extension to the fully extended TQFT, which is the same thing as extending to open-closed TQFT. Now, it's good to assemble these summed amplitudes into one big linear transformation by considering all possible ingoing spatial manifolds and all possible outgoing spatial manifolds. And so if we take all those A of x ins, x outs, we get one linear transformation, which is an endomorphism on the tensor algebra of the sum over x of z of x, where the sum over x here is the sum over all smooth connected d-1 manifolds considered up to diffeomorphism. And you can prove that the set of smooth connected manifolds of a given dimension up to diffeomorphism is a countable set. So this is a countable sum of finite dimensional vector spaces, so it makes sense, and we can take its tensor algebra. Now, actually, because we're summing over the bordisms, the amplitude descends to an endomorphism of the symmetric algebra of the sum over x of the seed TQFT. And I'll call that symmetric algebra the Fock space of the seed TQFT. So now the splitting property is the following. If I take the ground field to be the complex numbers, then we could put an inner product structure on the Fock space of Z, and we find that there exists an inner product space I'll call W, such that there's a linear transformation from the Fock space of Z to the Fock space of W, such that this total amplitude is phi adjoint. I wanted to put a dagger there, but Microsoft PowerPoint won't let you put a dagger without going through a lot of trouble. So I'll be using star for the adjoint with respect to the inner product. Okay, so one comment about my convention for composing linear combinations, linear transformations in this talk. So there's a canonical isomorphism of Hom V1, V2 with V1 dual tensor V2. So now if I have 2 linear transformations, T1, 2 from V1 to V2 and T2, 3 from V2 to V3, then I'm going to write the composed linear transformation by taking the second one on the right. Usually people take the convention that it's written on the left, but it's a little nicer to write it on the right. So T1, 2, T2, 3 is the linear transformation, the composed linear transformation from V1 to V3. And the way I want you to think of it for a calculation I'll do later is I take the tensor product, which lives in this product of 4 vector spaces, and then I just use contraction on V2 and V2 dual to map to V1 dual V3. Okay, so A bar is phi star. Let me make some comments on this splitting formula. So first of all, A bar need not be positive definite in the examples that we look at. And even if the existence is somehow trivial, I'm not sure if it is or not, but if the existence is trivial, then explicitly finding a splitting space W and a phi in examples, at least for Anindya and me, seem to be a little non-trivial. W is not unique. I could replace W by a direct sum of copies of W, and I could replace phi by a direct sum of copies of phi, weighted by the square root of some probability distribution. There might be a minimal splitting space in the following sense. There might be a splitting space, Wm and phi m, such that if I have any other splitting, then there's a map that makes this diagram commute. I haven't seriously tried to prove whether or not there is such a minimal splitting space, but it would be a nice thing to know if it's true. Okay, now I'm going to spend the rest of the time looking at a lot of examples to illustrate this splitting property. So maybe now is a good time for questions if there are any. Let me just make sure people are still there. Yes, people are still here. Okay, good. Okay. Let's see. Oh dear. Okay, from current slide. Let's see what happens there. No. Okay. Whoops. No, that worked. Okay. All right. So let's look at one-dimensional TQFT. And to be specific, one-dimensional unoriented TQFT. So now the TQFT is determined by just a finite dimensional vector space, which is the value on a point, and a symmetric non-degenerate bilinear form, B from V tensor V to the ground field, which is what we associate to this bordism that goes from 2 points to the empty set. So then the Fock space of Z is what I'll call the Fock space of V, which is just the symmetric algebra of V. And we could, in principle, we should talk about various completions and functional analysis aspects of that, but we did not study that in detail in our paper. So we'll just consider literally the symmetric algebra on V. Although we're going to find infinite sums, so a formal element. We're going to find that we're going to be working with formal elements in the symmetric algebra of V. All right, so let's start computing amplitudes by taking x in and x out to be the empty set. And so what are the bordisms from the empty set to the empty set in one dimensions? Well, they're just disjoint unions of circles. So the value of the TQFT on a circle is the dimension of that vector space V. If I have n circles, n disjoint circles, I get the dimension to the nth power, but because I'm dividing by the automorphism group I mentioned before, we divide by n factorial, and so that exponentiates in a nice way. So now it's useful to introduce what I'll call the Hartle-Hawking vector and the Hartle-Hawking covector. So the Hartle-Hawking vector is the sum of nothing to something. So mathematically, we can embed the ground field into this symmetric algebra, this Fock space, and then apply the total amplitude. And then the image of the canonical element 1 and the ground field is some vector, which I'll call the Hartle-Hawking vector. And the Hartle-Hawking covector is the dual. Conceptually, it's the sum of anything goes to nothing. So we apply our total amplitude from the Fock space to the Fock space, and then we project onto the scalars. And so the composition of those two defines a dual vector on the Fock space, which I'll call the Hartle-Hawking covector. So now let's compute in the simplest possible example. Let's take the dimension of V to be 1 and the ground field to be C. So then remember the TQFT requires a bilinear form, but we can choose a vector, a basis vector such that its norm square is 1. And then I claim that the Hartle-Hawking covector is given by this simple formula. So you see that, as I mentioned before, we're going to look at formal elements of the symmetric algebra of the dual space of the vector space. So we have an infinite sum here. And you notice the combinatorial factor, 2n factorial over n factorial 2 to the n. Well, let's consider 4 points going to nothing. So what we have to do is we have to pair them with this bilinear form, and we can pair them this way, or this way, or this way, and that should remind you of Wick's theorem. And so the 2n factorial over n factorial 2 to the n is the combinatorial ways of pairing up points into pairs if I have 2n points. Now, because we have this non-degenerate bilinear form, there's canonical isomorphisms between V and V dual, and we can use that to change the number of ingoing and outgoing points. So the basic idea is if I have some amplitude A24, where I've summed over all bordisms, then I could tack on this bordism to change one of the outgoing lines into an ingoing line, and algebraically that corresponds to acting with B upper dual. So if I do that, then this is the total amplitude in this very simple case. So this is indeed an element of this symmetric algebra V dual tensor V, and so that's the endomorphism of the Fock space of V. So now let's look at the splitting property. So I mentioned Wick's theorem before, and one way of looking at Wick's theorem is that it just says that this combinatorial factor is a certain Gaussian integral, written here. That's an integral of the real line. So let's introduce these elements of L2 of R. L2 of R is going to be our splitting space. And the inner product in L2 of these wave functions is 0 if n plus m is odd. And it's this combinatorial factor if n plus m is even. So therefore, we have, if I write this formula for phi here, then it's the work of a moment to take phi dagger and contract the psi n and psi n dagger and produce that formula I wrote before. Okay, and all of this generalizes to the dimension of V bigger than 1. So here's a nice formula that applies for arbitrary vector space V. What I've done here is I've taken a vector V in the V, and I've applied the Hartle-Hawken covector to what I call the exponentiated diagonal. So e to the V is 1 plus V tensor V over 2 factorial plus etc. And so I can at least formally apply the Hartle-Hawken covector to that. And the simple formula for what that is given here. But then you see the Hartle-Hawken covector is multilinear and totally symmetric. So it's determined by its values on the diagonal. So this formula implicitly determines the entire Hartle-Hawken covector. And then by applying the B upper dual, we get the total amplitude. The results can also be extended to oriented one-dimensional theory. In that case, you simply have a single vector space. It's the value of the functor on a positively oriented point, and on the negatively oriented point, you get the dual space. In this case, well, as I said, the splitting space is not unique, but one example, if you look at the formulas, one natural one that jumps out at you is L2 of the torus. Okay, now let's talk about the two-dimensional closed TQFT. So if I consider closed two-dimensional oriented topological field theory, then I think it's a very well-known result that the theory is completely determined by applying the functor to the spatial circle S1. And that's a vector space C, which, because of the sewing axioms, has to be a finite dimensional commutative Frobenius algebra. So this is a result that goes back to remarks made long ago by these people and others. The Frobenius structure comes by looking at the disk as a bordism from an ingoing circle to the empty set. And so under the functor Z, that corresponds to a trace or a linear transformation from C to the ground field. And then because of the so-called S cobordism construction, it's easy to show that the bilinear form that you define by multiplying and taking a trace is a symmetric non-degenerate form. And I'll discuss the open-closed case a little bit later. That's more complicated. Now, even very good experts still go around saying that this is just a folk theorem. But in fact, a complete proof of the relevant sewing theorems, including the equivariant case and the open-closed case, was in a paper I wrote about 20 years ago with Graham Siegel. So now there are several different cases we can consider. We can consider the case where we're only looking at closed strings, circles, as in and outgoing manifolds. And then the semi-simple algebra, the Frobenius algebra might be semi-simple or non-semi-simple, and those are two very distinct cases. In the semi-simple case, Anindya and I worked out everything for closed and open. In the non-semi-simple case, we just worked out the splitting formula for examples, and we didn't even try for the open-closed case for the non-semi-simple Frobenius algebras. There are a number of confusing issues there. So let's begin by talking about the case where Z of S1 is semi-simple. So in that case, the Frobenius algebra is just a finite sum of one-dimensional algebras, which are generated by idempotents. They satisfy this algebra. And the entire data of the Frobenius algebra structure is the value of the trace on the idempotent, the epsilon sub x. So I'll call that theta x, and it's just some element, invertible element in the ground field. That's all we need. Now, Graham Siegel and I emphasize that one should probably think about this as a baby model of two-dimensional topological string theory, where the target space is just a finite union of points, which is the spectrum of this finite dimensional Frobenius algebra. And of all the various fields in string theory, the only one that survives is the dilaton, which should be identified with this Frobenius trace on the idempotent epsilon x. And in string theory language, what we're saying is theta x is the inverse square of what's called the string coupling. So the different points x are different universes. They're all disjoint, so we can have different string couplings in the different components of the universe. Now let's start computing the amplitudes. So if we talk about the bordisms from the empty set to the empty set, well, those are just closed Riemann surfaces. And because of the way we're dividing by the automorphism group, that's the exponential of the sum over the amplitudes for connected closed Riemann surfaces. So they have genus 0, 1, 2, and so on, because we're doing the oriented case. So that's easily evaluated in an arbitrary two-dimensional TQFT as the trace on 1 over 1 minus h, where h is the so-called handle adding element. So if you consider a one-hole torus with one outgoing circle, that's naturally a state in the Frobenius algebra. It's called H, the handle adding state, and that's the general result. In the semi-simple case, we can simplify this and say it's the sum over exponential of the sum over the universes of lambda sub x, where lambda sub x is this geometric sum of the string coupling. And we're going to see lambda throughout the talk, so you might want to take a moment to look at that formula. So it's expressed in terms of the Frobenius trace, theta over 1 minus theta inverse. All right, so things get a little more interesting when we look at the amplitude for taking two disjoint union of two circles to the empty set. So what is that? Well, for simplicity of exposition, let us take the Frobenius algebra to be one-dimensional. So that means phi1 and phi2 are both proportional to the idempotent epsilon, complex numbers z1 and z2. And let's first consider bordisms with just one connected component. So what do they look like? They look like what I wrote here, where we can multiply phi1 and phi2 and take the trace, or we can we can multiply in some number of the handle adding element. So from that, it's straightforward to show that the amplitude here takes phi1 tensor phi2 to z1, z2 times lambda, where lambda, again, is the geometric sum of the string coupling constant. And similarly, if we consider bordisms with just one connected component and n ingoing circles, the same argument applies. You get the product of the z's and a single factor of lambda, which is the geometric sum of the string coupling. Now let's return to the case of two ingoing circles. So in addition to these bordisms with one connected component, we have bordisms with two connected components, and then we can add the handle adding element to either of those two components. And so the contribution of these bordisms, when summed up, is z1, z2 lambda squared. So altogether, the total amplitude, the summed amplitude applied to phi1, phi2 is z1, z2, e to the lambda. That factor of e to the lambda is for all those disjoint connected closed surfaces we could add in, and then lambda plus lambda squared. And Marolf and Maxfield recognized this polynomial as something called a Bell polynomial. So let me remind you what the Bell polynomial is. So the nth Bell polynomial is a polynomial in n variables, and it's a polynomial that counts the ways a set of n elements can be partitioned. So the coefficient of x1 to the k1, x2 to the k2, and so on, counts the number of disjoint decompositions of a set with n elements into k1 subsets of cardinality 1, k2 subsets of cardinality 2, and so forth. And we'll be particularly interested in the case where we put all of the x's equal to lambda. In that case, this thing is also known as a Touchard polynomial. So why is this Bell polynomial relevant? Well, if you think about a bordism of n disjoint circles going to the empty set, you can split it into connected components, and there will be connected components with j ingoing circles, and they will have, there will be, k sub j connected components with j ingoing circles. Now, each connected component, as I mentioned before, will give, when summed over handles, gives a factor of lambda. So Bn of lambda is exactly the right thing to compute here. So the upshot is that this is the Hartle-Hawking covector in this very simple case where the Frobenius algebra is dimension 1. So now if we apply that U-shaped bordism to turn ingoing circles into outgoing circles, then here's the full summed amplitude. This is the total amplitude. So it is the amplitude for ni ingoing circles and n out outgoing circles. So it's all summarized by this. And now the Touchard polynomials satisfy a very nice identity, which I've written here. E to the lambda times Bn of lambda is the sum from d equals 0 to infinity of lambda to the d over d factorial d to the n. That's an identity which was used extensively in the Marolf-Maxfield paper, and we will also use it, although we'll interpret it slightly differently from what they said. So here again is the formula for the total amplitude, and now we can substitute this expression. And so we write the total amplitude this way, and I've written it this way so that you see that we can start to move things that involve the ingoing circles to the left and things that involve the outgoing circles to the right. And in some sense, D is like counting some a sum over some kind of intermediate states. So I did that because now that motivates the splitting formula in this case. So to give a splitting formula, we need an adjoint. So we need a sesquilinear form. And a natural sesquilinear form. We didn't consider the arbitrary sesquilinear form. We probably should have. But a natural one to consider is one such that this is true. So the adjoint of epsilon is theta times epsilon dual. And so in this case, the splitting space will be the Fock space of C. And we find that for theta real, but not necessarily positive, we can write A bar as phi phi star, where phi is explicitly given by this formula. So let me take a moment to demonstrate this splitting. So you see, if we take the tensor product of phi phi star, so think back to what I said about how I'm composing linear transformations. So if I take the component, the tensor product of phi with phi star, I get a sum over 4 integers. You see, phi is a sum over 2 integers, L and D. If I take phi tensor phi star, I get a sum over 4 integers. And then in the middle, you see epsilon to the d ingoing and epsilon dual to the d outgoing. So if I contract the inner two factors, that puts d inner equals d outer equals d, and that recovers A bar so long as theta is real. Okay, so that proves the splitting formula in this case. Now, in this case, there's a nice relation to coherent states in the Heisenberg representation of, in the Stone-von Neumann representation of the Heisenberg algebra. So let's consider the standard Heisenberg algebra, bosonic Heisenberg algebra, and there's a standard Stone-von Neumann representation. So we choose a vector, a vacuum vector annihilated by A, And then we can make an orthonormal basis by acting with a dagger to the dth power and normalizing it. So let's call that ket vector d. And that will correspond to the element epsilon over the square root of theta to the d in the symmetric algebra. So then you can define what's known as a coherent state. And if you introduce the number operator, a dagger a, then this Touchard polynomial is nothing other than the expectation value of the number operator to the little nth power in this coherent state. So with that in hand, we can write a formula, we can reinterpret, write another formula for our total amplitude, which is very suggestive. So to write that formula, let me introduce an operator I'll call the universe annihilating operator. So it's an operator from the splitting space W to C dual tensor W, and in the basis, it's explicitly given by this formula. And C creation is the universe creation operator. It goes from W dual to W dual tensor C, and in an explicit basis, it's this formula. So now I claim that the total amplitude. So if we apply this idea that the Touchard polynomial is just this expectation value, then it's not hard to see that the total amplitude is an expectation value inside this coherent state in blue of this operator. So the total amplitude, of course, is an element of a linear transformation on the Fock space of C. So this is, if you like, an operator valued inner product. We're tracing out the stuff in blue to leave an operator in red. And so the way I like to think of this is that in some sense, W is the Hilbert space of a dual quantum mechanical system to the quantum gravity theory. So if I calculate amplitudes in this space W, I get operators, which are the operators that describe the amplitudes of the quote quantum gravity theory. One of the reasons I find this interesting is that it resonates with some ideas I thought about a few years ago, where I was trying to formulate something I called quantum mechanics with non-commutative amplitudes. So I want to just digress for 3 slides about what that is. So in standard quantum mechanics, we model states. To model states, we often use a Hilbert space, and then the inner product on Hilbert space is the complex numbers, is valued in the complex numbers. In quantum mechanics with non-commutative amplitudes, the idea was, well, can we generalize quantum mechanics so that we have an inner product which is valued not in the complex numbers, but in some C-star algebra, or possibly W-star algebra. When I wrote my paper, I only used C-star algebras, but Tom Mainero has since convinced me that I made a mistake, and really I should have phrased everything in terms of W-star algebras. But I'm going to say C-star algebra here. So anyway, what we're saying is we're entertaining the possibility that psi should be in a Hilbert C-star module instead of a Hilbert space. And the problem I set myself in that paper I wrote was, how in the world are we going to formulate a Born rule in that case? Because we can't just take the norm square of the amplitudes. Well, first, what is the Born rule? The Born rule pairs states and observables to give you a probability density on the real line, which is the probability of measuring of your output being valued in some specified range of values. So first of all, what are the observables? Well, we start by looking at the adjointable operators, operators for which this holds in our Hilbert module. And the adjointable operators form another C-star algebra B. And then what I eventually realized is that, well, actually, sorry, this part is obvious. So the QMNA observables are just the self-adjoint elements of B. What took a little bit of thought was to realize that a good way of defining a state is to take a completely positive unital map from B to A. And then in order to formulate a Born rule, what I also eventually realized was that we needed not just a state and an observable, but a third piece of data, which is a state on the C-star algebra A. And with that triple, there was a natural way of combining them to get a probability distribution on the real line. And you could think of that construction as constructing a family of quantum systems over a non-commutative space whose, quote, space of functions is A. And using that, you can reinterpret various constructions in quantum information theory in terms of non-commutative geometry. So, end of digression. The excuse for this digression was that we can write those quantum gravity amplitudes in terms of an operator-valued inner product. Back to this formula here. Okay, so now let's get back to the main development. So I'm just giving lots of examples of the splitting property. So let's look at open-closed two-dimensional TQFT. So in open-closed TQFT, that's the extension to the fully extended case. And again, for simplicity, we'll consider the oriented and semi-simple bordisms. Oriented bordisms and semi-simple Frobenius algebras on the circle. So now the in and out manifolds are disjoint unions of circles and oriented intervals. And the intervals should be thought of as one morphisms in a category of manifolds with corners. And now the intervals have boundary conditions at the end. And as Graham and I pointed out, the right way to think about this is that A and B are objects in a category of boundary conditions. And if we apply the functor to this interval with boundary conditions on the end, we get the Hom space in that category, or in more physical language, the open string state space with boundary conditions A and B. So now the surfaces are two morphisms in a two category. And the boundary of those morphisms really consists of three separate components. There's the usual in and outgoing boundary. So in this case, the ingoing boundary is two intervals in one circle in red. The outgoing boundary is one interval in purple. But then there are boundaries where we have to connect the endpoints of the intervals. And Graham and I call those the constrained boundaries. Those are in dotted green here. You can also modify your bordism category to include closed constrained boundaries. And so altogether, there are three conceptually distinct kind of boundaries. There are the in and outgoing boundaries of circles and intervals. There are the constrained boundaries connecting in and or out endpoints to in and or out endpoints of intervals. And there are the closed constrained boundaries. And there's some very confusing stuff in the quantum gravity literature, which I traced back to the fact that they weren't being very careful about the conceptual distinction between these different kinds of boundaries. I won't dwell on that because I don't think this audience has participated in those puzzles. Okay, so the splitting formula in the simplest case goes like this. I'll take the closed string Frobenius algebra to be one-dimensional. I'll take all the constrained boundaries to be labeled with a single boundary condition, which I call A. So our open string space is OAA, so in fact it's an algebra. There will be no closed constrained boundaries, and all of the in and out manifolds will be intervals. So to write amplitudes, then we have to introduce the open string coupling, which is just the square root of the closed string coupling. So you have to, there's another piece of data here, which is a choice of square root. And we find that mu has to be real, so the closed string coupling has to be positive, and then there's a splitting, where in this case, phi is a map from the symmetric algebra of the open string state space to L2 of a vector space E and A. So I have to explain what E and A is. So there's a condition in the open-closed TQFT called the Carty condition, which implies that the open string state space, which is an a priori an algebra, is in fact a full matrix algebra. So it can't be a direct sum of matrix algebras. And so since it's full matrix algebra, we can associate an integer n sub a to it. And here, E sub n sub a is the vector space of NA by NA Hermitian matrices. So I'll just flash this formula. So we have a very explicit formula for the splitting map, phi. But the only thing I want to stress here is that it involves a matrix model integral. over NA by NA Hermitian matrices. So now I want to talk a little bit about generalization to the equivariant case, to two-dimensional Yang-Mills. Well, first of all, let's suppose our gauge group is a finite group. That's the G equivariant case that Graham and I discussed in detail, actually. The bordism category is the category of principal G bundles. We now replace the Frobenius algebra by something Graham and I called a Turayev algebra. We won't need the details of what that is. The sum over bordisms splits into two parts. We sum over bundles, and then we sum over topologies of surfaces. But the sum over bundles is just the process of gauging, so it simply replaces C by a semi-simple Frobenius algebra, which I'll call C orbifold. And so we're back in the previous case. So more or less automatically, we have the generalization to the G equivariant theory with a finite group G. Things are more interesting when we consider a compact connected simple Lie group, because then it's not quite a topological field theory anymore. Two-dimensional Yang-Mills theory is not quite a topological field theory. The morphisms are surfaces with a total area A, which is additive under gluing. The state space is the space of class functions in L2 of G. For the Yang-Mills part, tensor the Frobenius algebra. So an orthonormal basis would be this, where R runs over the unitary dual, the irreducible representations of G, and chi R is the character. So then if we look at the vacuum-to-vacuum amplitude, well, for a fixed surface, it's a sum over the unitary dual, which I've given here. And then we sum over genus, and now because we're summing over bordisms, I interpret that as an integral over the area. So that's the kind of expression we need. And for this to make any sense at all, we need, interestingly, to introduce a cosmological constant, lambda naught. The measure for integrating over the area A is an interesting question, and I'm being agnostic about it. I'm just putting in A to the P. And I imagine that because I imagine that integrating out matter of various kinds would leave you with a partition function that depends on the area as just some simple power. So here's the vacuum-to-vacuum amplitude, and now you can sum over G and integrate over A, and you get this expression right here, sum over lambda R. Lambda R is given explicitly here, and then that sum converges for large enough real P, and I expect it admits an analytic continuation in P so that we can continue to possibly other interesting physical values for P. And then we evaluated the Hartle-Hawking covector in this theory, and so it's given by this expression. And so we could compare that result with the result for the semi-simple 2D closed case, and they look very similar, and that strongly suggests that there will be a factorization with the splitting spaces, again, the Fock space of the state space on the circle. Let me comment briefly on 3 and higher dimensions. We'd love to extend these ideas to 3-dimensional TQFT, but to put it mildly, the classification of manifolds is much more difficult. For example, the vacuum-to-vacuum amplitude would be a sum over connected closed diffeomorphism types of 3 manifolds, and you apply the TQFT amplitude to that 3 manifold. Among those 3 manifolds is S1 times Riemann surface, in which case Z of Y, by general principles, is given by the dimension of the state space on a surface of genus G. And in the standard TQFTs, that grows with G, and the sum is irretrievably divergent. You could ask yourself if there are TQFTs where the state space vanishes for sufficiently large genus G. And in a discussion with Sergey, he pointed out the answer is no. If C of sigma G vanishes for any genus G, then all the amplitudes vanish. So that leaves us with a big question. Is there a way to modify the domain and or codomain categories to produce interesting examples in bigger than 2 dimensions? So let me summarize. For suitable parameters of our TQFT, the total amplitude has a splitting of this nature. I showed you a bunch of examples. Anindya and I also worked out examples of non-semisimple 2D TQFTs. The splitting persists, although it takes some ingenuity to find the splitting space in the splitting. There are potential conceptual interpretations of this formula involving holography and quantum mechanics with non-commutative amplitudes. There are future directions, things that we didn't do. The general non-semi-simple case, closed and open, other tangential structures, unorientable manifolds, spin and pin manifolds, and so on. It'd be very nice to extend this to topological string theory, and a splitting formula for JT gravity, which is not topological. A splitting formula for JT gravity would have very interesting implications for the ongoing discussion about the role of ensemble averages in ADS-CFT. Now, final 2 slides or so. Something I worry about is whether the existence of a splitting formula is deep or a trivial consequence of linear algebra. The reason it might be trivial is roughly goes as follows. The total amplitude is symmetric under exchange of in and outgoing boundaries. And any symmetric, at least in finite dimensions, any finite dimensional complex symmetric matrix can be written as phi transpose. I wasn't able to convince myself that there was a rigorous version of this in our case, but there might be. So the final thing is what to do about d greater than 3. But before I finish, I just want to quickly advertise an upcoming paper with Roman Gecko, who is applying for jobs, and Time Mainero, who could also use a job. These are 2 very good people. And we're going to very soon be putting out a paper where we formulate 3 examples of 2 categories related to the spin chains and matrix product states. And so 1, 2 category is made out of the building blocks of matrix product states. We call them matrix product factors. Another has to do with von Neumann bimodules with a distinguished point. And a third is a 2 category of normal, completely positive maps. So if you find those subjects, and there are adjoint equivalences between these 2 categories. So if you find that subject interesting, keep an eye out. So thanks for your attention.
Thank you very much.